There's a curious quality to the thermal performance of a rammed earth wall. In the text, The Memory of Rock, Understanding Rammed Earth, by Gokul Salvadi, we get a clear picture of how this simple mass of Earth manages heat in a way that feels almost active, nearly intelligent. It all really starts with a physical experience. Imagine it's the middle of a hot day, and you place your hand on the outside of a rammed earth wall. It's warm, of course, from the sun, but then you walk inside and touch the interior face of that very same wall. It's surprisingly cool. Now come back later, maybe at midnight. The air outside is cool now, but that interior wall surface, it's releasing a gentle warmth. The heat from midday has just now finished its journey through the wall. And right there, that's the central point. The wall isn't acting as a barrier in the way we usually think of one. It's not simply stopping the heat. Instead, it's absorbing it, holding it, and then releasing it, but on a very significant time delay. So what's the mechanism here? What creates this delay? Well, it's a process that's rooted in the fundamental physical properties of the material itself. The formal term for this effect is thermal lag. It's a measurable property. It's the capacity of a material to take in heat energy, hold on to it for a while, and then let it go over a period of hours. The main driver behind thermal lag is density. As you can see here, rammed earth is a very dense material. It's right up there with concrete, and it's much denser than, say, brick or wood. This high density means there's just a lot of physical stuff, a lot of mass in a given volume. That allows it to absorb a huge amount of heat energy before its own temperature really starts to rise. It effectively soaks up the heat. And for a standard 1 foot thick or 300 millimeter rammed earth wall, that delay is typically between 8 and 12 hours. Now that's not a minor lag. It's a half-day shift in when the peak outdoor heat finally makes itself felt on the indoor surface. And this 8 to 12 hour lag lines up almost perfectly with the 24-hour daily cycle. The sun's heat hits the wall's exterior most intensely around 2 p.m. That wave of energy then travels slowly through the mass, arriving at the interior surface somewhere between 10 p.m. and 2 a.m. That's precisely when the outside air temperature has dropped and a little bit of warmth is actually welcome. By morning, the wall has released its stored heat and is cool again, ready to start the whole cycle over. But this elegant, self-regulating system is entirely dependent on one external factor. Its effectiveness really hinges on the climate that it's placed in. This brings up a critical question. Is a high-mass wall a universally effective strategy for thermal comfort? The physics of the system itself actually provides the answer. The entire cycle relies on the wall's ability to reset itself. It has to have a cool period during which it can release or discharge the heat that it absorbed during the day. If it can't get rid of that heat, the system fails. This chart illustrates the importance of what's known as the diurnal temperature swing. In a climate with a high swing, let's say it's 35 degrees during the day and drops to 15 at night, the wall has a long, cool period to offload all its stored heat. But in a low swing climate, like a humid region where it might be 33 degrees by day and only drop to 28 at night, there's no significant cool phase. The wall can't fully discharge, so it just accumulates heat day after day until it becomes a permanent radiator that you can't turn off. So as you'd expect, rammed earth performs best in places with that big temperature swing. Arid deserts, Mediterranean climates, and high-altitude tropics. It becomes a liability in the humid tropics, where it's always warm. It also creates a problem in cold winters because without some kind of exterior insulation, its mass just acts as a heat sink, constantly pulling warmth out of the building and into the cold ground and air. This leads us to a really fundamental distinction in how we control heat in buildings. And that's the difference between using mass and using insulation. You can think of thermal mass as a kind of thermal battery. It absorbs, stores, and later releases energy. Its main function is to delay heat transfer. Insulation, on the other hand, is a barrier. Its job is to resist heat flow, to slow the rate of transfer at all times. So you see, insulation works best in steady conditions, while mass works with cyclical conditions. So these aren't competing technologies. They're just different tools for different thermal challenges. The choice of which one to use or how to combine them depends entirely on the climate you're building in. So let's return to the human experience inside one of these buildings. The physics we've been talking about produces a distinct feeling of comfort that actually goes beyond just that time delay effect. The mass of the wall doesn't just delay heat, it also dampens it.
As this chart shows, a large 20-degree temperature swing on the outside might only translate to a much smaller, say 4-degree swing on the interior surface. The mass essentially flattens the peaks and troughs of the daily temperature wave.
And what people often perceive as comfort in a rammed Earth structure is this feeling of stability. It's the absence of drastic temperature fluctuations. The interior environment remains remarkably steady, regardless of the extremes happening right outside.
There's also one final, more subtle mechanism at play here, and that's radiant temperature. Our sense of thermal comfort is affected not just by the air temperature, but also by the temperature of the surfaces that surround us. We exchange heat with them. So at night, the warm interior wall is radiating gentle heat towards your body. This allows you to feel comfortable even if the air temperature is a little cooler. In the morning, the now cool wall does the opposite. It starts absorbing radiant heat from your body, which makes you feel cooler, often without any real change in the air temperature. It's a passive system that interacts directly with you. So in the end, the performance of the wall is a direct conversation with its environment. The material itself is a constant, but its value as a thermal regulator is determined entirely by the climate. If that daily rhythm of heating and cooling is right, the wall works. If it isn't, it simply doesn't.